Hey everyone, and welcome to this explainer. Today we're going to tackle a concept that literally powers everything around us, from the screen you're staring at right now to the lights in your room, and yeah, even that phone in your pocket. We're diving into the fundamentals of electricity, specifically looking at how current, voltage, and resistance all interact. It's an absolute cornerstone of physics, and we're going to break the whole thing down step by step. Let's get right into it. So, have you ever actually stopped and wondered why a light bulb glows brighter when you crank up the current? Or, why a flashlight kind of slowly dies out when the batteries run low? It's something we see every single day, right? But the invisible physics happening inside that tiny wire, it's honestly fascinating because that changing brightness isn't just magic. It's governed by a very specific, unbreakable set of rules. And to really understand exactly why that bulb glows the way it does, we need to look at the law that controls the whole shebang. Section 1. What exactly is Ohm's Law? Okay, so here's the formal textbook definition. Ohm's Law states that the current flowing through a conductor is directly proportional to the potential difference across its ends, provided the temperature remains constant. Now, that potential difference is just what we usually call voltage, and I really want you to pay attention to that last part. The law is incredibly reliable, but it has boundaries. Temperature is absolutely the key physical condition that has to stay exactly the same for this rule to hold perfectly true. But let's ditch the textbook jargon for a second and look at what that actually means. It's essentially a simple, direct proportion. Assuming our temperature isn't changing, if you have more voltage, it pushes harder, and bam, more current flows through the circuit. On the flip side, less voltage means a weaker push, so less current flows. That direct proportional relationship, that is the absolute heart of Ohm's Law. If you get this, you pretty much understand the fundamental behavior of electricity in any basic circuit. Now, to turn this whole proportional concept into math we can actually use, we have to introduce a constant. And that constant is R. So our equation shifts from a proportion to the legendary formula V equals I times R. Just to be crystal clear on our terms here, V is the potential difference, or voltage, which we measure in volts. I is the current, measured in amperes or amps. And R? Well, R is this brand new variable we've just brought to the party. That's resistance, and it's measured in ohms. Which brings us to Section 2, understanding electrical resistance. So what is resistance anyway? Basically, it's the property of a conductor that actively opposes the flow of electric current. I like to think of it as a physical obstacle, or kind of like an internal friction inside the wire itself. The electrons are desperately trying to move through the material, but the material is literally fighting back, making it tougher for them to squeeze through. Literally every material has this property to some degree. It's actually a good thing, too. It's what keeps the current from just blowing out and flowing infinitely fast. It's honestly a perfect balancing act. If you have higher resistance, it acts as a massive obstacle, which means it allows way less current to flow. Lower resistance, though, that provides a nice, easy path, allowing a lot more current to get through. The wild part is, the voltage could be pushing with the exact same strength in both scenarios. But it's the resistance that actually acts as the bouncer and decides how much current ultimately makes it past the velvet rope. And that resistance isn't just a random number. It actually depends on 4 specific physical factors. First up, the length of the conductor. Second, the area of its cross-section, so basically how thick or thin the wire is. Third, the specific material the wire is actually made of. Some metals let electricity glide right through, while others put up a real fight. And finally, temperature. Remember earlier when we heavily emphasized temperature in the definition of Ohm's Law? This is exactly why. Because if the temperature changes, the internal resistance changes. And if the resistance fluctuates, that perfect proportionality of Ohm's Law gets completely thrown out the window. Section 3. The Ohm's Law triangle. Okay, so if you ever find yourself needing a quick way to rearrange that V equals IR formula, this little spatial arrangement is an absolute lifesaver. It's a classic study hack. You just draw a triangle. The V, for voltage, sits proudly right up there at the very top. Then down at the bottom, you place the I for current and the R for resistance right next to each other. Here's how it works. You literally just cover up the value you're trying to find with your thumb, and the layout instantly hands you the formula. Want voltage? Cover the V, and you see I and R next to each other, so it's I times R. Need current? Cover the I, and you've got V over R. Looking for resistance? Cover the R, and it's V over I. It is practically a foolproof way to make sure you always have the right formula on hand without having to do any mental gymnastics or complex algebra on the fly. All right, let's actually put this to the test with a quick example. Imagine you're looking at a basic circuit. You know the voltage is pushing at 12 volts, and the total resistance in the circuit is 4 ohms. So what is the current? Well, using our trusty triangle, we're looking for current, or I, so V over R. We just take our 12 volts divided by our 4 ohms of resistance, and boom, that gives us exactly 3 amperes of current. By simply plugging those values into the relationship defined by Ohm's Law, the math basically just solves itself. Super easy, right? Moving on to Section 4, graphing voltage and current. So what does this look like in the real world when scientists actually map it out? Well, when engineers test what's called an ohmic conductor, which is just a fancy term for material that strictly plays by the rules of Ohm's law, they usually plot the voltage against the current on a graph. And the result? It is always a perfectly straight line passing directly through the origin. This visualizes that exact direct proportionality we established at the very beginning. As voltage increases, current increases at the exact same proportional rate. There are no weird curves, no sudden, unpredictable spikes, just a perfectly straight, super reliable line.
All right, section 5. Let's recap.
So, to wrap this explainer up, let's run through the ultimate mental cheat sheet. Ohm's law is the fundamental rule that governs how voltage, current, and resistance relate to one another. It all hinges on that golden formula, V equals I times R. Remember, resistance is the physical obstacle opposing the current flow. Crucially, for this elegant law to actually work, we absolutely need a constant temperature. And finally, when you graph an ohmic conductor, it's always going to give you a perfectly straight line. But before we sign off, I want to leave you with a bit of a mind bender. Since a constant temperature is so absolutely vital for Ohm's law to work predictably, think about this. If temperature changes severely alter resistance, how do extreme environments, like, I don't know, the freezing cold, empty vacuum of outer space, or the scorching, fiery heat of a distant planet, how does all that affect the incredibly delicate electronics we launch up there in satellites and rovers? Seriously, how do engineers even begin to design functional circuits when the fundamental rules of resistance are constantly shifting under those extreme conditions? Food for thought. Thanks for joining me on this explainer, and keep questioning how the universe works.